Hi, everyone. Thanks for tuning in. This presentation is focused on decision support for urban planners and other municipal stakeholders. It describes a prototype software system by which decision makers can visualize the impact of changes, including planning interventions. Residents of cities depend on infrastructure systems ranging from electricity to healthcare. In many cases, particularly where cities are undergoing densification, legacy infrastructure systems are stretched to the limits. Changes in demand patterns can occur in a number of ways. For example, population growth can result in increasing demand. Various planning decisions, such as zoning, can also result in increased demands that may strain legacy systems. As engineers and computer scientists, we believe that there are potential tools that can help decision makers to not only forecast demand patterns, but to visualize the consequences of interventions. So, who are we? Well, first, this project is really the brainchild of Mark Fox, Associate Director of Research at the School of Cities at the University of Toronto. Steve Easterbrook, Director of the School of the Environment and a Professor of Computer Science. And yours truly, James Williams, PhD student and sometimes law professor. So we're going to delve into the perspective that we adopted in this project. We're going to describe the model, the software prototype, and a number of suggestions for future work. We're going to consider changes within cities according to two categories. First, we have evolutionary changes, which are not the result of decision making. The graph on the right shows the population of London over time. Physical processes such as erosion may also affect infrastructure assets. Second, we have interventions. These include zoning changes, maintenance activities, and the development of new infrastructure systems. A good example of an evolutionary process driving change is the Thames Tideway project. The population of London eventually exceeded the capacity of the existing sewer system. An example of an intervention is the development of Mirvish Village in Toronto. An existing set of low-rise commercial buildings is being replaced by a high-density residential complex that will put additional strain on legacy infrastructure systems. According to municipal engineers, Toronto is facing major issues with electricity capacity. It has the largest number of condominium projects of any city in North America. These large residential buildings have very high demands for electricity since water must be pumped to each unit. The big worry is managing peak demand. Already, a lot of Toronto's lines and transformer stations are at their design limits. What works for sprawl and suburban development doesn't work for high-density environments where buildings go upwards. In the case of sprawl, infrastructure is laid out first and buildings are added later. But in a high-density environment, buildings are added on top of legacy infrastructure. How can we develop software tools to aid urban planners and other municipal stakeholders in dealing with these issues? Our first step was to commit to a set of design decisions. First, we focus on resources as well as some key services like education. As a result, we're mostly concerned with capacity constraints. Second, we model each infrastructure system as a network, in particular a flow network. Third, we model interdependencies between networks. Infrastructure systems can depend on each other in a number of ways, including physical, informational, and financial dependencies. Since we focus on resources, we're interested mainly in physical dependencies, in which one network supplies a resource that another network requires. For instance, a water system might require electricity to run pumps. Fourth, our software must operate at district scale. A lot of planning decisions take place at the level of districts. Mirvish Village and the Waterfront Toronto Sidewalk Labs collaboration are two examples. Finally, our software should run in GIS systems, since urban planners are already familiar with them. We partition the area of study into spaces and systems. Spaces include blocks, which contain buildings, and lots, which contain houses. Various types of buildings exist, including hotels, hospitals, laundromats, and residential apartment buildings. Apartment buildings will contain one or more households, while a house contains a single household. Each household generates demands for resources such as water and electricity, taken over a 24-hour cycle. Buildings also generate demand according to their type. For instance, a laundromat has heavy demand for water. Apartment buildings are a little bit special in that they combine the building's demand, which represents the basic minimum resources needed to function, with the aggregate contributions of the people who reside within it. So the aggregate building demand is taken by summing up all the demands for the residents and for the building itself. Once demand profiles have been loaded for each building and house, they are propagated out into the network in order to find the load on each network component. The precise details of the propagation mechanism are beyond the scope of this presentation, but they can be found in the reference below. Some services are better represented by catchment areas. These include educational facilities like schools and emergency response. In this case, a building or house that falls within the catchment area simply contributes to the aggregate demand for resources. Our emphasis is on a key set of systems including gas, water, electricity, and sewer systems. Demands are on an hourly basis, and we make no effort to model physics. Most infrastructure systems except schools are treated as simple flow networks. Lastly, transportation is a little bit more complicated. Transport models generally aren't granular enough to model individual parcels. As a result, we provide a simplification that we'll describe later. So let's finally take a look at the prototype. It was written as a standalone application in C++ and OpenGL. Data is drawn from a number of sources, as we show in the next slide. The workflow begins with OpenStreetMaps. We import a street map into Esri's City Engine, which is used to generate blocks and lots. From City Engine, we export files to a custom C++ application. Demographic information can be obtained from a standard land use transport model. This screenshot shows how we export data from OpenStreetMaps. City Engine allows us to visualize blocks and lots. It also allows us to edit the map manually to correct errors in the OpenStreetMaps data. Python is used to export data from City Engine into our own custom C++ application. While it can render in 3D, it turns out it's very confusing to visualize multi-layer networks in this fashion, so we tend to stick to two-dimensional representations. This image shows our application's view of the area around Mirvish Village in Toronto. In this representation, parcels and lots are in green, while buildings are in light purple. Infrastructure systems show up as overlays on this basic block and lot model. Infrastructure systems are created manually. Edges can be directed or undirected, pipes can have capacities, and each building is assigned a type that determines its demands. This image shows the same portion of Toronto augmented with a water network. To reduce confusion, each infrastructure system is color-coded. Physical interdependencies are created by the analyst manually. This image shows a water system that depends on electricity to power pumps. Here's the water network and electricity network side by side. You'll notice the pump on the left is connected to a node A on the electricity network. In this fashion, demand for water induces demand for electricity. Once we've constructed a model, we can do some interesting things. For instance, we can take a building or lot and visualize the demand generated by it. We can color code buildings and lots by demand, allowing us to get a high-level view of where demand is coming from in the model. We can use these tools to explore different scenarios. For instance, here's a view of demand generated by a set of buildings and houses. What we're going to do is substitute the building in the middle of the model with a larger apartment building that generates far more demand. In this second scenario, the building in orange generates 2,000 units of demand per hour. You can see how the load on the network has increased significantly. One of the most useful views is to look at residual capacities. In this screenshot, each pipe segment is labeled with a color code indicating the amount of residual capacity left. The introduction of the new residential complex has stressed some of the pipe segments, as you can see from the orange colors. As mentioned previously, transportation is different from water or electricity. Transport models don't tend to work at parcel lot level, meaning we're left with approximating transport behavior. For each lot in the model, we choose a set of nodes at random from the street graph. We then find paths to those nodes and register the demand against the corresponding segments. There are many opportunities for future research. Let's talk about 4: user interface issues, data sources, transportation modeling, and activity-based modeling. User interface work is pressing. The presence of multiple interlocking infrastructure systems makes it difficult to create a clean method of visualization. Our initial use of 3D graphics seemed to hinder more than help, as it's confusing to keep track of all the different layers in a 3D perspective. Data issues are also critical. Most cities don't have comprehensive repositories of infrastructure information in a form that's suitable for integration into models. As a result, some researchers are investigating proxy methods whereby street networks are used to infer the presence of other infrastructure systems. Another issue concerns boundaries. Any district-level model can capture only a small subset of a city, including its infrastructure components. Models must have a robust method of accounting for these boundaries. In our work, we place supply nodes and demand nodes at appropriate locations. However, computation of supply and demand requirements is not straightforward. Ultimately, data from utilities should be incorporated. As mentioned previously, transport modeling is a special case. Transport models typically operate at zip code level, which is not granular enough for our needs. This constraint arises from the use of survey data to build transport models. One alternative is to use GPS-based transport surveys. These can have small sample sizes, though. Agent-based approaches in which synthetic populations are created from GPS data are probably more promising. The approach that we used in our initial prototype was to model demands based on building profiles and household profiles. These are generated from survey data. A better approach, and one that's more in tune with transport modeling, is to have activity-based methods in which activities generate demands. This sort of approach would necessitate the use of a demographic model, albeit it would allow us to integrate with land use and transport systems. The computational requirements could be high, however, and we wouldn't want to give up our ability to work within GIS frameworks. From Mark, Steve, and myself, I'd like to thank you for listening and enjoy the rest of the conference.